Hey everyone, welcome back. Today we are talking about an absolutely essential topic in programming, especially in languages like C++, the heap in memory management. Let's dive straight in. First, let's quickly define what the heap is. In computer science, the heap is a region of a program's memory where dynamic memory allocation takes place. This memory is managed by the operating system and is used when you don't know ahead of time how much memory you will need. In contrast, we also have something called the stack. The stack is fast and automatically manages memory, but it's limited. When you need more flexible, longer-lived memory, you use the heap. In C++, when you allocate memory on the heap, you usually use the new keyword. In this code, we dynamically allocate an integer on the heap. The new keyword asks the operating system for enough memory to hold an integer and returns a pointer to that memory. The important thing to remember is that memory you allocate with new stays allocated until you explicitly free it. If you forget to free it, you create a memory leak. Memory leaks are dangerous because they can make your program consume more and more memory over time, possibly crashing your system. To free heap memory, you use the delete keyword, like this. This releases the memory so that it can be reused. Now, if you allocate an array on the heap, you use a slightly different syntax. Here is an example. This creates an array of 10 integers on the heap. And when you are done with it, you need to free it using delete square brackets instead of just delete. If you forget the square brackets, you might not properly free the entire array, which would cause undefined behavior. Now, you might be wondering, why not just use the stack all the time? The answer is limits. Stack memory is very limited, usually just a few megabytes. Heap memory is much larger, potentially gigabytes, and can handle much bigger dynamic data structures like large arrays, linked lists, trees, and so on. But heap memory is slower to allocate and deallocate because it requires system calls under the hood. Also, you have to manually manage it, which can introduce bugs. In modern C++, we often avoid row new and delete by using smart pointers like std_unique pointer and std_shared pointer, which automatically manage heap memory for us. Here is a simple example with std_unique pointer. When the unique pointer goes out of scope, it automatically deletes the memory it owns. This helps prevent memory leaks. Another thing to keep in mind is fragmentation. As you allocate and deallocate different sized blocks on the heap, it can become fragmented over time. Fragmentation means you have free memory, but it's spread out in little pieces instead of in one big continuous block. This can make it hard to find a big enough block for a large allocation, even though enough memory technically exists. Some systems use heap managers or garbage collectors to help deal with fragmentation and leaks, but in C++ you are responsible for it. Let's quickly review. Heap memory is dynamic. You use new to allocate and delete to deallocate. If you forget delete, you leak memory. Arrays need new square brackets and delete square brackets. Use smart pointers in modern C++ to make life easier. And that's a basic introduction to the heap in memory management. Understanding how the heap works will make you a much better programmer and will help you write faster, safer, and more efficient C++ code. Thanks for watching and see you on the next video. Hey everyone, welcome back to the channel. Today we are diving into a really important concept in systems programming and C++ development. Memory alignment in memory management. Let's break it down step by step. First, what exactly is memory alignment? In simple terms, memory alignment refers to arranging data in memory according to certain boundaries. These boundaries are usually powers of 2, like 2, 4, 8 or even 16 bytes. The goal is to make memory access faster and more efficient for the CPU. You might be wondering, why does alignment even matter? Well, CPUs are optimized to read and write data from memory at specific addresses. If data is not properly aligned, the CPU might have to perform extra work to read it. This can lead to slower performance and even hardware faults on some architectures. Now, let's look at a simple C++ example. Suppose we have this structure. At first glance, you might think this struct takes up 6 bytes. 1 byte for A, 4 bytes for B, and 1 byte for C. But that's not the case. Because of alignment, it usually takes 12 bytes. Let's step through it. Char A is 1 byte, so it starts at address 0. Int B needs to be aligned to a 4 byte boundary, since address 1 is not divisible by 4. The compiler inserts 3 bytes of padding after A to align B at address 4. Then B occupies 4 bytes. Addresses 4 through 7. Char C comes next at address 8. Now, depending on the system, there might be 3 more bytes of padding after C to make the size of the struct a multiple of the largest alignment requirement, which is 4 bytes. You can check the size of this struct by writing this code. This usually outputs 12, so memory alignment isn't just about the variables themselves. It also affects the overall size of data structures. Now, let's talk about how we can control alignment in C++. One way is using the alignS keyword introduced in C++11. For example, this tells the compiler to align aligned example to a 16-byte boundary. This can be very useful for SIMD operations or when working with hardware that requires specific alignments. Another important thing is that improper alignment can cause undefined behavior. On some architectures like ARM, trying to access misaligned memory can cause a crash. When you allocate memory manually, you might need to ensure proper alignment yourself. Before C++17, this was tricky. Now, with C++17, you can use std-aligned alloc. Here is an example. This allocates 64 bytes of memory aligned to a 16-byte boundary. Don't forget, whenever you use aligned alloc, you need to free the memory with free. Now, you might be thinking, can alignment cause fragmentation? Yes, it can, especially if you align a lot of small objects to large boundaries. Memory gets wasted between allocations. This is why memory pools and custom allocators often try to optimize around alignment issues. Let's quickly summarize. Memory alignment improves CPU performance. Misaligned memory can lead to slowdowns or crashes. Compilers automatically add padding to structures to ensure proper alignment. You can control alignment manually using alignS or aligned memory allocation functions. And remember, always check the documentation of your target platform. Different CPUs have different alignment requirements. Alright, that's it for today's video. If you found this helpful, don't forget to like and subscribe for more deep dives into C++ and systems programming. Thanks for watching and I will see you next time. Hey everyone, welcome back. Today we are diving deep into a fundamental part of memory management, how malloc and free work. Even though we are usually coding in C++ on this channel, it's important to understand these C-style functions because they are building blocks underneath the abstractions we use every day. Let's get started by thinking about how memory is organized. When a program runs, memory is typically divided into several segments. There is the stack, the heap, the text segment, and the data segment. The stack is used for static memory allocation, like when you declare variables inside a function. The heap, on the other hand, is where dynamic memory allocation happens, and that's where malloc and free comes in. Now, what does malloc actually do? The function malloc, short for memory allocation, is used to request a block of memory from the heap. The syntax looks like this. Here we are asking the system to give us enough memory to store one integer. Let's think step by step about what happens internally. First, when malloc is called, it checks if there is a block of free memory big enough to satisfy the request. If there is, it reserves that block and marks it as in use, then returns a pointer to the start of it. If there isn't enough memory available, malloc returns a null pointer. Now notice that malloc does not initialize the memory it gives you. The memory could contain any random leftover data. It's purely raw memory. In C++, we usually prefer using new, but behind the scenes, the memory allocation part of new often ends up calling malloc or a similar low-level function provided by the operating system. Okay, but now that we have dynamically allocated memory, we also need to be responsible for freeing it when we are done. That's where free comes in. Let's say we have this code. We can later call this. It tells the system, hey, I'm done with this memory. You can reclaim it for future use. Internally, free takes the pointer you pass it, finds the metadata that malloc stored, usually just before the block you received, and updates its internal bookkeeping to mark that block as free. If you forget to call free, you will cause a memory leak. That means the program holds onto memory it doesn't actually need anymore. Over time, especially in long-running programs, memory leaks can add up and cause the system to slow down or even crash. It's equally important not to double free memory, meaning don't call free on the same pointer twice. That can corrupt the heap structure and cause undefined behavior, which is often very difficult to debug. Here is an example of proper usage. Notice how we check if malloc returned a valid pointer before using it. That's a good habit. Now, there is one more thing. Once you call free, the pointer you had still exists, but it points to memory you no longer own. This is called a dangling pointer. A good practice is to immediately set your pointer to null pointer after freeing it, like this. That way, if you accidentally try to use it later, it will be easier to catch the mistake. Because dereferencing a null pointer usually triggers a clear and immediate error. So to summarize, malloc reserves memory on the heap. Free releases it back to the system. Always check if malloc succeeded. Always free exactly once. Set pointers to null pointer after freeing them. Understanding malloc and free is crucial, even in C++, because smart pointers like stud unique pointer and stud shared pointer manage memory safely, but underneath they are built on the same ideas. Alright, that's it for today. I hope you now have a clearer understanding of dynamic memory allocation. Thanks for watching and I will see you next time. Hey everyone, welcome back. In today's video, we are diving into a key concept in memory management, the stack. If you are programming in C++ or any other language, understanding the stack is essential. So let's walk through it step by step. First off, what exactly is the stack? Well, think of the stack as a special region of memory that your program uses to store data temporarily. It's called a stack because it behaves like a real-life stack of plates. You always add plates on top and you always remove plates from the top. This is known as last in, first out, or LIFO. When you run a C++ program, the operating system gives it a certain amount of memory. Part of that memory is reserved for the stack. It's managed automatically. You don't have to allocate or free memory manually for most stack operations. Let's look at an example. Suppose we have a simple function. When greet is called, two things happen. First, a stack frame is created for this function. A stack frame contains all the function's local variables. In this case, number and message are both stored in the stack frame. As soon as greet finishes running, its stack frame is popped off the stack, and all the memory used by number and message is automatically reclaimed. You don't need to manually delete anything. That's the beauty of the stack. It's fast and self-cleaning. Now, let's get a bit deeper. Each time you call a function, a new stack frame is pushed onto the stack. Each frame holds not just local variables, but also information like the return address. Basically, where the program should jump back after the function is done. So, if you have nested function calls like this, when function A calls function B, a stack frame for function B is placed on top of function A's stack frame. When function B finishes, its frame is popped, and control returns to function A. But what happens if the stack gets too big? That's called a stack overflow. It usually happens when you have deep or infinite recursion. For example, every time infinite recursion calls itself, a new stack frame is added. Eventually, you run out of memory and the program crashes with a stack overflow. Now, you might be wondering, what can you put on the stack? typically small, short-lived data. Primitive types like int, char, float are perfect for the stack. Small structures or simple objects can also go on the stack, but large objects like huge arrays or complex data structures are better placed on the heap, another area of memory, because the stack has limited space. In C++, if you write this, the variable x is stored on the stack, but if you do this, here the pointer p itself is on the stack, but the integer it points to is on the heap. You have to manually delete heap memory to avoid leaks, but stack memory is automatically managed. Finally, why do we care about the stack? Because it's extremely fast. Allocating memory on the stack is basically just moving the stack pointer down, and deallocating is moving it back up. No complicated bookkeeping, no fragmentation. That's why many critical, performance-sensitive parts of programs use stack allocation as much as possible. However, you must be careful. Don't return pointers or references to local stack variables. They will be invalid once the function exits, like this. Here, temp will be destroyed when bad function returns. The pointer you get will point to garbage memory. Always remember, stack memory is temporary. Alright, that's a basic but solid overview of stack in memory management. Thanks for tuning in, and I will see you in the next video. Hey everyone and welcome. Today we are talking about dependency injection in C++. What it is, how to do it, and why it actually matters in real-world code bases. Let's start with the basics. Dependency injection, or DI, is a way to give an object the things it depends on, rather than having it create them itself. That's it. It's a simple idea, but it solves some really important problems in architectures, like tight coupling, hard to test code, and hidden dependencies. Let's look at a small example. Imagine you have a class game that needs a renderer to draw graphics. You might write something like this. Seems fine, right? The problem is game is tightly coupled to renderer. You can't change the rendering behavior without modifying the game class. You can't substitute a mock renderer for testing, and you are managing memory manually. That's a red flag in modern C++. Now let's refactor this using dependency injection. Instead of creating the renderer inside game, we pass it in from the outside like this. Now the game class depends on a renderer, but it doesn't construct it. That responsibility has moved outside. That's dependency injection. So why is this better? First, we can now easily swap out the renderer. Maybe we have a console renderer or a null renderer for testing. And now we can do this. This means game is testable, it's flexible, and you've separated the concerns. Game runs the game, and someone else figures out what kind of rendering to use. Dependency injection supports something called inversion of control. Instead of high-level modules controlling the construction of their dependencies, the control is inverted. The configuration happens outside, often at program startup. That makes your components reusable and decoupled. Now, there are different ways to do dependency injection. What we just did, passing dependencies via the constructor, is called constructor injection. It's the most common and usually the cleanest. There is also setter injection, where dependencies are passed in through a setter function after construction. Setter injection is useful if you want to change the dependency at runtime, but it comes with the risk that the object is only partially initialized after construction. So use it when that trade-off is worth it. There is also interface injection, where a dependency provides a method to inject itself. This is rare in C++ and mostly used in more dynamic languages. Now let's talk about manual versus framework-based dependency injection. In languages like Java or C#, there are full-blown dependency injection containers that automatically wire up your dependencies. In C++, we rarely need that. Manual dependency injection is usually enough. and it gives you more control over performance and memory. That said, you can write a lightweight factory or service locator in C++ if your project is large enough and you want to manage object lifetimes more dynamically. Let me show you a small example of building a factory function. Now, the creation logic is outside the game class. That keeps your business logic clean and focused. So to recap, dependency injection in C++ means passing an object's dependencies from the outside, instead of constructing them internally. This gives you better testability, lower coupling, clearer object lifetimes, easier to swap or extend components. And all of this adds up to more maintainable code, especially as your project grows. One common anti-pattern you will want to avoid is the hidden dependency. That's when a class depends on something but doesn't say so in its constructor. For example, here, game depends on the logger, but it doesn't say so. That makes the class harder to reason about and harder to test. A better design is to inject the logger, even if it's a singleton. Now, everything game depends on is visible. Alright, that's a wrap on dependency injection in C++. It's not just a buzzword, it's a practical tool that leads to more modular, cleaner and testable code. If you want to see more real-world patterns like this, hit like and subscribe. And please let me know in the comments which C++ pattern you want to see next. Catch you on the flippity flip! Hey everyone, welcome back. In today's video, we are diving into a very cool feature introduced in C++ 20, Stud Source Location. If you've ever needed to log or track where something happens in your code, like a specific line or function, this feature is going to be super helpful. So what exactly is Stud Source Location? At its core, Stud Source Location is a utility that allows you to get information about the current source code location. The file name, function name, line number, and column number. It's particularly useful for debugging, logging, or any kind of diagnostic information where you need to know where something in the code was executed. Let's start by looking at how to use it. Here we have a simple log message function that logs a message along with where it was called from. The Stud Source Location current is a specific static member function that captures the current location when the function is invoked. Now let's see it in action. When you run this, the output might look something like this. So instead of hard coding file names or line numbers in your logging code, Stud Source Location provides them automatically. But it's not just about logging. It can be extremely helpful for tracing errors, performance diagnostics, and other situations where knowing the context of where a function was called is important. A great example is in custom assertions. Imagine you are writing an assert macro. Now, if an assertion fails, you will know exactly where it happened in your code, complete with file name, line number, and function name. To recap, Stud Source Location is an awesome new tool in C++ 20 for tracking where code is executed. It can make debugging and logging much easier and cleaner. And because it's so easy to use, it's something you will likely find yourself reaching for in many situations. Thanks for watching. If you enjoyed this video and found it helpful, don't forget to like, share and subscribe. Catch you on the flippity flip! Hey everyone, welcome back. Today we are diving into a super important topic in C++ and programming in general. Stack versus heap in memory management. Let's break it down step by step. First, let's talk about the stack. The stack is a region of memory that stores temporary variables created by each function. Think of it like a stack of plates. You can only add or remove a plate from the top. Similarly, in memory, the last variable you created is the first one that gets removed. In C++, when you declare a variable inside a function like this, the variable x is stored on the stack. When my function ends, x is automatically removed from the memory. You don't need to do anything. This is called automatic storage. The stack is super fast because it only has to move a pointer up and down. But there is a catch. The stack is small. If you use too much stack memory, you can get a stack overflow. Now, let's move on to the heap. The heap is a region of memory used for dynamic memory allocation. You manage it manually. If you need a variable to live beyond the scope of a function or you need a large amount of memory, you use the heap. In C++, we use new to allocate memory on the heap. Here, p is a pointer stored on the stack, but the actual integer it points to, the 20, is stored on the heap. Important difference. When you are done with heap memory, you have to free it manually, using delete. If you forget to delete, you have a memory leak, which can cause your program to eat up memory over time. One way to visualize this is, the stack memory is like a stack of plates, where you always remove or add plates at the top. Heap memory is like a big storage room where you can throw stuff anywhere, but you have to remember to clean up after yourself. Now, let's look at a quick comparison. The stack is fast but small. The heap is slower but much larger. The stack memory is automatically managed. The heap memory must be manually managed. Another thing to keep in mind. Accessing heap memory is slower than accessing stack memory, because it involves more steps for the CPU. In real-world C++ code, you try to use the stack as much as possible, because it's efficient. You only reach for the heap when necessary. There are also smart pointers in C++, like std_unique pointer and std_shared pointer. These pointers help manage heap memory automatically. Here is an example. In this case, smart p will automatically delete the memory when it goes out of scope. You don't have to manually call delete. This helps avoid memory leaks and makes your code safer. Another important point. When you pass variables to functions, stack variables are usually passed by value, making a copy unless you use references. Heap allocations are typically passed around using pointers or smart pointers. Quick tip. If your object is small and doesn't need to survive outside the function, use the stack. If it's large or needs to live longer, use the heap. To wrap up, stack memory is like a quick, short-term storage. Heap memory is like a long-term storage, but you are responsible for managing it. Understanding the difference between the stack and the heap will make your C++ code more efficient and bug-free. Alright, that's it for today. If you found this helpful, don't forget to like and subscribe for more C++ content. See you next time. Hey everyone! Today we are going to talk about something that's both simple and powerful in C++, std system. So what exactly is std system? In short, it's a function that lets your C++ program run system commands, just like you would in a terminal or command prompt. It's defined in the cstd_lib header, and you can use it like this. That string you pass to std system gets sent to the underlying shell. On Windows, that's usually cmd.exe, and on Unix-like systems, it's typically bin/sh. Let's take a quick example. Suppose you want your program to list all files in the current directory. You could do something like this. When this runs, your program will temporarily pause and run the command. Whatever that command prints to the terminal, you will see in your program's output. So why is std system useful? Well, it can be quick and a dirty way to hook into tools that already exist on the system, like compiling code, launching other programs, copying files, or even calling Python scripts. It saves time when you don't want to write C++ code to do those things manually. But, and this is a big but, you have to be careful with std system. First, there is a performance hit. Spawning a shell and executing commands can be slow compared to native C++ solutions. Second, it can be dangerous. If you are passing user input directly into std system, you can open yourself up to command injection vulnerabilities. That's where someone could insert malicious shell commands into your input and potentially take control of the system. Also, because it's OS dependent, code using std system isn't always portable. A command that works on Linux might fail completely on Windows, and vice versa. So when should you use std system? Use it when you need something quick and you are sure it's safe and cross-platform compatibility isn't a priority. But for anything serious or security sensitive, look into native alternatives like C++ file system library, std-thread, or process management libraries like boost.process. That's it for now. Std system is simple to use, but handle it with care. Thanks for watching, don't forget to like and subscribe. Catch you on the flippity flip! Hey everyone, welcome back. In today's video we are going to explore one of the most underrated but powerful tools in modern C++, std string view. If you have ever passed strings around in your programs and worried about unnecessary copies or performance issues, this video is for you. Let's think step by step and see what string view does, and why it's such a game changer. So what is std string view? It's a non-owning, read-only view of a string. Basically, instead of holding the actual data, it just holds a pointer to a string and its length. This means you can refer to any string-like data, std strings, string literals, character arrays, without copying the contents. Here is a quick example. Now you can call greet with different types. No need to convert everything to std string or deal with overloads. String view handles it all. Let's talk performance for a second. Normally, if you pass a std string by value, it creates a copy. Even passing by const reference means the function expects a std string. But with string view, you are passing a tiny, lightweight object, like passing a pair of pointers. Fast and efficient. But here is the catch. Since string view doesn't own the data, you have to be careful not to use it after original string goes out of scope. So always make sure the underlying string outlives the string view. Another cool thing, you can do slicing super easily. That's much more convenient than messing with substrings and copies. To sum it all up, std string view is a fast, flexible way to work with string data without owning it. It improves performance, reduces copies, and makes APIs more generic. Just remember, it doesn't own the data, so use it wisely. Thanks for watching. If you learned something new today, hit that like button and subscribe for more ++ tips. Catch you on the flippity flip! Hey everyone, and welcome back to the channel. In today's video we are going to talk about a super useful but often overlooked feature in modern C++, the nodiscard attribute. If you have ever written a function that returns a value but sometimes forgot to actually use that value, this feature is for you. Let's break it down step by step. So what does nodiscard actually do? In simple terms, it's an attribute that you can apply to a function or even to a type, which tells the compiler, hey, the return value of this function is important, don't ignore it. If you do ignore it, the compiler will give you a warning. Let's look at a basic example. Now, if you call calculate and just discard the result like this, the compiler will warn you because you probably meant to do something with that value. Why is this helpful? Well, it helps catch bugs early. Maybe you are calling a function that returns an error code or a result you need to process. If you forget to use the return value, your program might silently misbehave. Let's take another example using a class. Now, any function that returns error code will also trigger a warning if the result is ignored. That's perfect for things like error handling, where you really want developers to check what went wrong. This feature was introduced in C++ 17 and in C++ 20 it got an upgrade. You can now include a custom message. If someone calls do something and ignores the result, the compiler won't just warn, they will see your message explaining why it matters. Let's think step by step here. You are writing a low-level function. It returns success or failure as a bool. If someone forgets to check that, you might crash later and not know why. By adding nodiscard, you are putting a safeguard in place. To sum up, nodiscard helps make your code safer and your intentions clearer. It tells users, don't ignore this, it's important. Simple, effective, and a great habit to get into. Thanks for watching, and if you found this helpful, be sure to like and subscribe. Catch you on the flippity flip! Hey everyone, welcome back to the channel. In today's video we are diving into one of the coolest and most flexible types introduced in C++ 17, std variant. Let's think step by step. Imagine you want to store either an int, a float, or a std string in the same variable. In older C++, this usually meant reaching for pointers, unions, or writing some custom class. But now with std variant, it's clean, type safe, and way easier to manage. So what is a variant? At its core, std variant is a type safe union. It can hold one of several types, and the compiler keeps track of which type it currently holds. Think of it like a box that can hold either an int, a float, or a std string, but only one at a time. Here is a basic example. In this line, data can hold an int, a float, or a std string. Let's set a value. Each time, the type inside data changes. But how do we read the value? You can use std_get to access the value. But here is the catch. If you try to get the wrong type, it throws std_bad variant access. So it's best to check what's inside first. Using std holds alternative. Or even better, use std_visit. This will call the lambda with whatever type is currently held. It's clean, modern, and works with all types in the variant. Let's consider a use case. Imagine you are building a config system, and the setting might be an int, a float, or a string. A variant handles that perfectly, without complex inheritance or custom wrappers. To summarize, std variant brings flexibility while staying type safe. It's perfect for modeling data that can be one of many types, and it pairs beautifully with std_visit for clean access. That's it for today's video. If you found this useful, hit like, subscribe, and let me know in the comments what feature you want to see next. Catch you on the flippity flip! Hey everyone, welcome back. In today's video we are diving into the world of STL containers, and specifically we are going to explore std unordered multiset. So what exactly is an unordered multiset? Let's think step by step. You might already be familiar with std set or even std unordered set. These are containers that store unique elements, meaning no duplicates allowed. But sometimes you do want to store duplicates. And you also don't care about the order of elements. That's exactly where std unordered multiset comes in. It's part of the unordered set header, and just like the name says, it's unordered, meaning it does not maintain any specific order. And it's a multiset, which means it allows duplicates. Let's look at a basic example. This code will output values, but not necessarily in the order you inserted them. That's because it uses a hash table under the hood, not a sorted structure like std set. So why would you use unordered multiset? The big reason is performance. Since it's based on hashing, insertions, deletions, and lookups, all take constant time on average, O1. That's a big win if you are working with large datasets and don't need sorting. Another great feature is the duplicate support. Let's say you are counting how many times values appear, or storing items where duplicates are valid, like quotes or word occurrences. Unlike unordered set, this container won't silently discard your duplicates. Here is another example. Now nums will contain free 2's, because duplicates are perfectly allowed. You can also use functions like count to check how many times a value appears. So to recap, std unordered multiset is your go-to container when you want fast access using hashing, you need to store duplicate values, and you don't care about the order. That's it for today's breakdown. If you want to dig into the differences between this and other sets like std set or std multiset, let me know in the comments. Thanks for watching, don't forget to like, subscribe, and catch you on the flippity flip! Hey everyone, welcome back to the channel. In today's video, we are diving into std Tuple, one of the most flexible and underrated tools in the C++ standard library. Let's think step by step. Imagine you want to return multiple values from a function, like an int, a string, and maybe a float. Normally, you would have to define a struct or pass variables by reference, but with std Tuple, you can group multiple values of different types into a single object super easily. Here is a quick example. Just like that, you've created a single variable that holds an int, a string, and a float. No need for a custom type. So how do you access the value inside? The studget function uses a zero-based index to pull out the element you want. Easy and clean. Now, here is where it gets even cooler. Let's say you want to return multiple values from a function. You can return a tuple directly. And on the receiving side, you can unpack the tuple like this. That's called structured bindings, introduced in C++17. It makes working with tuples so much nicer and more readable. But that's not all. StudTuple also supports comparison, concatenation with StudTuple-cat, and even compile time introspection using StudTuple size and StudTuple element. Here is one more handy use case. Imagine you are dealing with function parameters of different types and want to store them together. You can just pack them into a tuple and pass that around. Also keep in mind, if you don't like typing out the full type name, you can use auto or studMakeTuple. C++20 also gives us tuple swap and better constexpr support, making tuples even more powerful. So to wrap it up, StudTuple is your go-to tool when you need to group multiple values of different types into one container, especially for returning multiple values cleanly from functions. If you found this helpful, make sure to like, subscribe and hit the bell for more C++ tips. Thanks for watching, catch you on the flippity flip! Hey everyone, welcome back. In today's video we are going to talk about studany, a powerful and flexible utility introduced in C++17 that lets you store any type of value in a type-safe way. Let's think step by step about what this actually means. Normally in C++, when you declare a variable, the type is fixed. An int can only store integers, a studstring holds strings, and so on. But what if you want to write a function or class that can hold anything, without knowing the type ahead of time? That's exactly what studany is for. At its core, studany is a type-safe container for single values of any type. It works a bit like a box. You can put anything in the box, but you need to know what's inside before taking it out. Here is a basic example. In this code we assign an int to a studany variable. To get the value back, we use studanyCast with the correct type. If you cast to the wrong type, it throws a bad anycast exception. Now here is something cool. You can assign any type. For example, so why would you want this? Let's say you are building a plugin system, a scripting interface, or even a UI where values can be of different types. Int, float, string, and so on. Instead of writing a separate logic for each type, you can use studany to store them in a uniform container, like a studVector containing studany types. But here is the catch. Because it's type erased, you lose compile time type safety. You have to manually cast it back, and if you get the type wrong, it will either throw or fail silently, depending on how you check it. So use it wisely. It's not a tool you want to use everywhere. But when flexibility is more important than strict typing, studany can be a lifesaver. To check the type safely, you can use value.type.name for debugging or use studanyCast to return a pointer that's null if the type doesn't match. Alright, that's a quick intro to studany. It's a clean and powerful way to work with dynamic types while still playing within the bounds of modern C++. Hope this helped. If it did, hit that like button. Catch you on the flippity flip! Hey everyone, welcome back to the channel. Today we are diving into something that's both super efficient and kind of underrated in C++. Bitset. If you've ever needed to work with binary data, flags, or just want a memory efficient way to store bits, then Bitset is your new best friend. Let's start simple. What is a bitset? In C++, Bitset is a fixed size container that stores bits, ones and zeros. Unlike integers, which also use bits under the hood, Bitset gives you direct control over each individual bit. You can set them, reset them, flip them, and even test their values, all with a clean and easy to use interface. Let's think step by step. Say you want to represent 8 bits. You can create a bitset like this. Now you have 8 bits, all initialized to 0. Want to set the third bit? Want to flip all bits? Want to reset everything to 0? You can also access bits just like an array. And here is a really nice feature. You can construct a bitset from a string or an integer. So why would you use bitset instead of something like int? Well, with bitset you get bit level control and built-in methods that make code easier to read and maintain. You can even count how many bits are set, or check if none are set. Another cool trick, you can perform bitwise operations directly. To sum it up, stud bitset is perfect when you want to work with a known, fixed number of bits efficiently, with clean syntax and full control. That's it for this video. I hope you learned something new. If you did, drop a like, maybe subscribe. Catch you on the flippity flip! Hey everyone, welcome back! In today's video we are diving into a super convenient feature introduced in C++20, stud format. If you've ever struggled with formatting strings in C++ using stud cout, printf or string streams, this one is for you. Let's start with the problem. Traditionally, formatting in C++ wasn't exactly elegant. You either had to use stud string stream, which is clunky, or the old printf style functions, which are type unsafe and prone to bugs. Wouldn't it be nice to format strings cleanly and safely like in Python? Well, with C++20 you can with stud format. Here is a simple example. Just like that, hello world gets printed. No need to mess around with streams or worry about types not matching format specifiers. Let's think step by step about what's going on here. Stud format takes a format string and any number of arguments. Inside the format string, you use curly braces as placeholders. Each curly brace is replaced by the corresponding argument in order. It's clean, it's readable, and it's safe at compile time. Now, what if you want to include formatting options? You can easily do it like this. Here, less than 10 left aligns the first value in a field of width 10, and greater than right aligns the second value in a field of width 5. This gives you tight control over output layout, perfect for building tables or logs. And the best part, it works with user-defined types too, as long as you implement a formatter. That gives you complete flexibility. You can even format numbers like this. This prints the number in hexadecimal with the 0x prefix. No manual conversion required. So why should you use stud format? Well, it's modern, safe, type-checked at compile time, and incredibly clean. It's part of the format header, and it's here to replace many of the old, clunky formatting techniques we've dealt with for decades. To wrap up, if you are using C++20 or later, stud format is an absolute game changer. It makes your code cleaner, safer, and more professional. That's it for today's video. Don't forget to like and subscribe. Catch you on the flippity flip! Hey everyone, welcome back. In today's video we are diving into something a little underrated but very useful. Stud placeholders. You've probably seen them used with stud bind, but maybe you weren't quite sure what was going on. So let's break it all down step by step. Alright, so what are stud placeholders? In simple terms, they are part of the functional header and are used with stud bind to create function wrappers. Kind of like pre-configured versions of functions where some of the arguments are already fixed and others are left to be filled in later. Let's take a simple example. Suppose you have this function. Now let's say you want to create a version of add where the first argument is always 10. That's where stud bind and stud placeholders come in. What this line does is create a new function object called add10, where the first parameter to add is fixed to 10, and the second is still open. Stud placeholders 1 means the first argument you pass to the new function. So now you've effectively delayed part of the function call. This is really useful when you need to adapt functions to fit into different APIs, especially ones that expect callbacks or function pointers with a specific signature. Let's think step by step about a real-world use case. Imagine you are working with a GUI library or some kind of event system that expects a function with just one argument, like a callback that takes a button ID. But your logic needs more context. You can use studbind with placeholders to sneak in extra arguments and still satisfy the expected signature. You can chain multiple placeholders too. Now it swaps the two arguments. Kind of cool, right? One thing to note. While studbind and studPlaceholders are powerful in modern C++, lambdas are usually the preferred way to do similar things. But for legacy code or quick adoptions, studbind still has its place. That's it for today. Now you know what studPlaceholders are and how to use them with studbind to build flexible, partial function calls. If this helped clear things up, give it a like and subscribe for more C++ tips. Catch you on the flippity flip! Hey everyone, welcome back to the channel. In today's video we are diving into one of the most essential tools for modern C++ developers, stud unique pointer. So what exactly is unique pointer? Let's think step by step. In C++ we often deal with dynamically allocated memory using new and delete, but managing memory manually can lead to bugs, especially memory leaks or double deletes. That's where smart pointers come in. And stud unique pointer is the simplest and safest of them all. A unique pointer is a smart pointer that owns a resource, and only one unique pointer can own that resource at a time. When the unique pointer goes out of scope, it automatically deletes the resource it owns. You don't need to call delete, it's all taken care of. Here is a quick example. We just created a dynamically allocated integer with the value 42, but there is no new keyword here. Make unique handles that for us. And better yet, we never need to call delete. Now, why is it called unique? Because it can't be copied. Only one unique pointer can own the object at any time. If you try to copy it, the compiler will throw an error. But you can move it. After this line, pointer no longer owns the resource. Pointer 2 does. This transfer of ownership is what makes unique pointer so safe. It enforces a strict ownership model. Let's look at a class example. This is clean and safe. If an exception is thrown later, you don't have to worry about leaking memory. Unique pointer will handle the cleanup automatically. Now here is a tip. Always prefer stud make unique over using new. It's safer, shorter and exception friendly. To summarize, stud unique pointer owns a resource exclusively. It deletes the resource when it goes out of scope. You can't copy it, but you can move it. It's perfect for managing memory automatically and safely. That's it for today's video. Unique pointer is an absolute must-know for modern C++ programming. If you found this helpful, don't forget to like and subscribe. And let me know what C++ topic you want to see next. Catch you on the flippity flip! Hey everyone, welcome back. In today's video we are diving into one of the coolest additions from C++ 20, stud span. Now, if you've ever passed around row pointers and array sizes in your code, you know it can be error prone and kind of messy. Stud span is here to clean that up. It gives you a lightweight, bounce-safe view over a sequence of elements, like an array or a vector, without actually owning the data. Let's break it down step by step. So what exactly is stud span? Think of it like a window or a view into an existing array or container. It doesn't copy anything, it just wraps the data and gives you safe, easy access to it. Here is a simple example. Now you can call this function with a vector, an array, or even a C-style array. See how clean that is? No need to pass a pointer and the size separately. And bonus, stud span knows its size, so it avoids out of bounds access. That's a huge win for safety. Let's think about a typical use case. Before stud span, you might have written a function like, then you would have to manually make sure that the pointer isn't null, the size is correct, and you don't read off the end. With stud span, all of that gets wrapped into a tidy, expressive package. A span can also refer to just part of a container. It even works with multi-dimensional spans, though that's a bit more advanced. Now keep in mind, std span doesn't own the data, so make sure whatever it's pointing to outlives the span itself. If the data goes out of scope, you are in trouble. To wrap it up, std span is an elegant, zero overhead way to work with continuous ranges of elements. It makes your function safer, cleaner and more flexible, all without sacrificing performance. That's it for this one. If you like this breakdown, give it a thumbs up and subscribe for more modern C++ content. Catch you on the flippity flip! Hello everyone and welcome to today's video, where we break down one of the exciting new features introduced in C++20, the Spaceship Operator, represented by this symbol. In this video I'll explain what this operator does, how it simplifies comparisons, and why it can be a game changer in writing cleaner and more maintainable code. Let's start with a bit of background. The Spaceship Operator is also known as the freeway comparison operator. Traditional C++ comparisons using operators like less than, greater than, and so on often lead to verbose code when implementing sorting algorithms, or even basic object comparisons. With the Spaceship Operator, the language provides a unified way to compare values. It's designed to return a value that clearly indicates whether the left-hand side is less than, equal to, or greater than the right-hand side. When you write an expression like this, the operator evaluates the relationship between the two operands and returns an ordering result. This result is typically one of several types of ordering categories, provided by the standard library, such as std strong ordering, std weak ordering, or std partial ordering. Each category informs the user of the precise nature of the comparison. For instance, if the operands are completely ordered with no ambiguity, std strong ordering is returned. Let's think step by step about how this works. Imagine you have two integers. In this case, since 5 is less than 10, the Spaceship Operator returns a value that indicates the relationship. This single operator replaces several lines of code that you might have otherwise written, like checking for equality first and then comparing which is greater or less. This reduction in verbosity not only makes your code cleaner, but also minimizes the potential for errors. Moreover, the Spaceship Operator enables the compiler to automatically generate default comparison operators for your user-defined types. By simply marking your class with the appropriate defaulting, you allow the compiler to deduce the proper behavior based on your members. Consider a simple class example. In this example, the operator first compares the x coordinates. If those are equal, then it moves on to comparing the y coordinates. This built-in logic streamlines the process of ordering objects. It's intuitive and saves valuable development time. That's it for today's video. I hope you now have a clearer understanding of how the Spaceship Operator works in C++ and why it's such an important addition to the language. Catch you on the flippity flip! Hey everyone, welcome back to the channel. In today's video we are going to talk about something that's simple but incredibly handy in C++. Std pair. If you have ever needed to return two values from a function, or just wanted to group two related items together, then std pair is something you should definitely know about. Let's break it down step by step. A std pair is a class template from the utility header that lets you store exactly two values, possibly of different types. It's like a mini container that holds two elements, first and second. Here is a basic example. In this example we create a pair where the first element is an int and the second is a string. Accessing the values is super easy using .first and .second. You can also use std make pair helper to create pairs without explicitly writing the types. C++17 made this even nicer by allowing deduction guides, which means you can just write like this, and the compiler figures out the types for you. Now let's think about how this is actually useful. Imagine you have a function that needs to return two values, like a result and a status flag. You can return a std pair instead of creating a whole new struct. Then when you call it, this is called structured binding, and it was introduced in C++17. It makes working with pairs even cleaner. Another great use case is when working with associative containers like studmap. When you insert a value, the return type is a pair, containing an iterator, and a boolean indicating whether the insert was successful. So, to sum up, studPair is a lightweight and powerful way to group two values together. It saves time, reduces boilerplate, and works great with modern C++ features like structured bindings. That's it for today's video. If you found this helpful, give it a like and don't forget to subscribe for modern C++ content. Catch you on the flippity flip!